Right. Okay, so I'll be taking over today because Dr. Sankar is flying to China for an AI event, right? Okay, so my name is Shaheen. I'm one of the TAs, right? I teach in Group 1. Okay, so today we'll be talking about list and tree processing, right? Right, so before we begin, right, I need to do a small recap. Right, so yesterday you learned about pairs, right? So at the beginning of this course, you learned about primitive data types, right? You learned about primitive data types. Now, can someone tell me an example of a primitive data type? Yeah, you learned about numbers. You learned about booleans and strings, right? Okay. So yesterday you learned about pairs. So pairs is an abstraction which helps you to combine primitive data types, right? And you also learned how to you also learned how to actually combine pairs together, right? So by nesting pairs together, you can form lists, right? Right. So that's what you learned yesterday. Um, okay. So just a review, right? Const p equals pair12. So pair is actually a binary function which takes in two values. This is the head and the tail, right? So head p acts as the first component and tail p acts as the second component, right? Okay. Right. And then you also learn about lists, right? Right. So a list, okay, this definition, right? It's important that you actually memorize this definition because the more you actually memorize the definition, it's actually easy for you to answer questions, right? Okay, so a list is either what? Null or a pair whose tail is a list. All right. So this is an example of a what? What type of definition is this? This is a recursive definition. Why? Because list is defined in terms of itself, right? Okay. So this is an example of a recursive definition. Okay. Right. So then there are three types of ways to actually display lists. First one is what's the first type or what's the first way of actually displaying lists? First one is box notation, and then the second one is list notation. Third one is box and point diagram, right? So I hope you guys are familiar because yesterday the reflection was about like drawing lists in box notation, list notation, and also box and point diagrams, right? Okay, good. Right. So then we need to actually refine this notion of a list because for now you had a list of arbitrary data types, right? But now we're going to refine the definition of a list. Now we're going to talk about lists of a certain data type. For example, we're going to talk about lists of numbers, right? So now we're going to talk about a list of a certain data type. Now, for example, we can talk about a list of a list of numbers, right? So a list of a certain data type, okay, is either null, same, right? Or a pair whose head is of that data type and whose tail is a list of that data type. For example, right? For example, you can actually, okay, a list of numbers is either null or a pair whose head is a number and whose tail is a list of numbers. Okay, so this is one example of a list of a certain data type, right? So a list of numbers is either null or a list of numbers is either null or a pair whose head is a number and whose tail is a list of numbers. Okay, so this is just one small refinement of the definition of a list, right? It's nothing much. Okay, right. So this need not be numbers only, right? It can be like list of strings is either null or a pair whose head is a string and whose tail is a list of strings. Is that okay? Is that okay to everyone? Yeah. Okay, I'll just erase this. Okay. Right. So for example, here you have a list of numbers, right? Right. So first example, can you see the? Yeah. So we have a list of numbers. For example, pair one, pair two. So list one, two, right? We have a list of booleans. We have a list of strings, and yes, the last one is actually a list which is empty. So an empty list can vacuously, we call it vacuously, contain anything. It can either contain numbers, it can contain strings, it can contain booleans, it can contain anything. Okay. So that's the difference between list A, B, and A, B, C, and D. So list D is null, empty list. So it doesn't really contain anything, which means you can say it contains anything. Okay, right. So that's a small tricky corner case. You don't need to worry too much about that, right? Okay, now before we come to this one, right? Right. So before we actually come to all the recursive stuff that we're going to do, right? Cool stuff, right? We need to talk about this thing called wishful thinking, right? Okay. Right. So visual thinking is a technique that you can use to solve any recursively defined problem, right? Visual thinking is a technique that you can use to solve any recursively defined problem. Okay. Right. So what's the first step? The first step to solve any recursively defined problem is to find out the base case, right? The second step is to reduce the problem to a smaller subproblem. Okay. Right. The second step is to reduce the problem to a smaller subproblem. The third step is to wish, right? This is a key step. Third one is to wish that you can solve the smallest subproblem by simply calling the recursive function on the smallest subproblem. Okay? Right. The fourth one is to combine the solution to the smallest subproblem to actually solve the larger problem. Right? So these four steps are really important. If you get these four steps, your practical exam is like a breeze, right? You can really close your eyes and do the practical exam. It's actually nothing much. So please try to understand these four steps. Okay? Right. So let's actually go to an example of where I demonstrate the power of this technique, right? Okay. So now the first example is the sum of the elements of a list. Oh, yeah. First one is sum of the elements of a list. So we want to write a function, right? Called sum that will take a list and return the sum of the elements in the list. So I'll just go down. There we are. Okay. Right. For example, right, if I have list 1, 2, this is a bit. So what I'm going to do is like this. So we have, can everyone see the board? Yeah. So we have XS list 1, 2, 3, 4, right? And we have this function that we're supposed to write. So function okay. So if I have this list, right, what would the result be? The result is equal to 1 plus 2 plus 3 plus 4. Okay, so that's if I have a list like this, the result of summing the list would be 1 plus 2 plus 3 plus 4, right? Okay. Right. So what's the first step? Fine, figure out the base case, right? Okay. Before we figure out the base case, I would like to actually reduce the problem to a smaller subproblem. Okay. Now look here, right? So we have a list, right? List 1, 2, 3, 4, and we need to sum the list. So that the answer would be 1 plus 2 plus 3 plus 4. So look at the second step. We want to reduce the problem to a smaller subproblem. Okay. Now if I look at the result, right? My goal is to reduce this problem to a small subproblem. I say that 2 plus 3 plus 4, right? 2 plus 3 plus 4 is nothing but the sum of the tail of the list, right? So can you see that I wanted to sum list xs, right? And summing list xx would give me 1 plus 2 plus 3 plus 4. I reduce the problem to a smaller subproblem by noticing that the rest of the sum comes from the tail of the list. Okay, so I reduce the problem to first solving sum on the tail of the list, and then using the answer to the tail of the list, I combine the head of the list to finally sum the entire list. Okay, so that's actually very important. The main important thing is I have a list. I want to sum the elements in the list. I reduce the problem size by noticing that that's the rest of the sum is actually summing the tail of the list. Okay, so that's the most important thing. Okay, so for example, now in this case, I would have the sum of a list, forget about the base case for now, is what? So this I can get by summing the tail of x's. Right? That I can get by summing the tail of x's, right? Okay. So now look here. Okay, so I want to sum x's. So I want to sum x's. That means 90%. Okay, the rest of the sum comes from the tail of x's. So that means I would have sum of tail of x's. Right? Okay, so I want to sum x's. Now that means I already have the answer to the tail, right? I already have this answer. So what's missing from my my final answer? What's missing from my final answer? 1. Okay, it is 1, but with respect to excess, what is that? Head of excess, right? So then you would have to return head of excess plus the sum of the tail of excess, right? Okay, now let's figure out the base case. So this is the general case, right? So what's the base case? Well, the base case is the simplest case. That means the case that you can solve without doing any recursion. So what's that? What's that case? Yes, if the list is empty, then yeah. Is there anything to sum? No, right? Okay, yeah. So then, okay, now we write the base case. So base case is actually pretty easy, right? So base case is so return is null excess. If it's null, then what should I return? 0. If it's not, then this one. Okay, so the most important thing is second step, right? You to reduce the problem to a smaller subproblem. That's the first step. And then you wish that you can solve the small problem. You wish that you can solve the smaller subproblem by simply calling the recursive function on the smaller subproblem. Now, can you see this, right? Can you see that the tail of excess and excess? So excess is a problem that we want to solve, right? And tail of excess is a smaller subproblem than the excess. Is that clear? Right? So tail of excess is a smaller subproblem than excess, right? So summing the tail is a smaller subproblem. Summing the tail of the list is a smaller subproblem than summing the entire list. So since we reduce the problem size, we can use this technique known as wishful thinking to simply call the recursive function on the smaller subproblem to solve the original problem. Okay, is that clear? Okay, I hope that's clear. Now, this is a very powerful technique. It may seem very innocent, but it's actually pretty powerful. So let's go into my examples to see why it's so powerful, right? Okay, so next question. Okay, before we go there, okay, so let me see. Okay, so length, we'll talk about that later, right? Okay, so now we're going to talk about appending to lists. Okay, now, okay, so again, second example, we want to write a function called append that will take in two lists and append them. Okay, right? So what does append mean? Append means actually combining them. Okay, so append means combining two lists together, right? Okay, now for example here, right? We have two lists, right? List 135 and list 24, right? So we have list 135 and list 24. So we want to append them. That means we want to combine the two lists, right? To get the following list, 135, 24. For example, these are the inputs, right? So we have 135 and 24. So we want to combine the two lists, right? We want to combine the two lists so that we can get what? 135, 24. Is that okay? Right. Okay, so since some of you can't see the board, right? I try to connect my computer. Okay, so I'll try to quickly connect to my computer because some people cannot see the board, right? 1 second. Okay, why is it not? Okay, never mind. It's not working. I'll just continue like this. Okay, right. So we want to append two lists together, right? So if you have list 135, list 24, we append them to get list 13524. All right, good. So now look here, right? Okay, so we have, so I hope this is okay, right? This is pretty easy. Okay, now let's go to the next one. So we have, XS list 1, 3, 5. And then we have YSS list 2, 4. And then we have result. Okay, right. So we have a function called append. Okay, right. So now look here, right? So the result, okay, so can someone tell me what the result should look like? List 1, 3, 5, 2, and 4. Okay, so what's the okay? So first step was to, okay, the first step was to figure out the base case, but you can actually swap it with actually reducing the problem size. Okay, so now we want to append two lists, XS and YS, to get this result list. Right? So 13524 would be 13524. Right. So now remember the step that we're trying to do is actually reduce the problem size, right? So the current problem is to reduce the append XS and YS to a smaller subproblem, right? Okay, now look here, right? If I look at the result, right, I see that 3, 5, and 3524 can be gotten by actually appending the tail of XS to YS, right? So can you see that? The tail of the result can be gotten by actually appending the tail of XS to YS. Is that clear? Okay, so can you see that I actually reduce the problem size? So I want to append XS to YS, and I look at the result, and I realize that the tail of the result, right? So this part actually can be gotten by appending the tail of XS to YS, right? So I can get this by append tail of XS to YS. Can you see that? Can you see that? Can you see this thing, right? Can you see that this is a smaller subproblem than appending XS and YS? Why is that? Because I reduce the problem size by 1 actually. I reduce the length of XS by 1 and kept Y the same. Can you see that I reduce the problem size? Right? Can you see that I reduce the problem size? So if I reduce the problem size, I can use a technique known as wishful thinking, right? Right? So what's wishful thinking? Wishful thinking means I can simply call the function on the small subproblem and it will automatically solve itself. All right. So since I actually reduce the problem size by 1, I can use this technique known as wishful thinking. So, right. So then that means my result, right, is composed by appending the tail of XS to YS. I reduce the problem size by 1. Therefore, I can use the technique known as wishful thinking to get this part, right? So then how can I get this one? Because I need to combine this thing with 1, right? How can I get this one? Yeah. So I already have this part, right? That is appending the tail of XS to YS, but this one is missing, right? How can I get that one? Sorry? Pair 1. Yes, correct. So pair head of XS to this answer, right? Right. So we need to pair the head of XS with this, right? Okay. Is that okay? Right? I hope it's clear, right? So can you see I reduce the problem size by looking at the answer. I realized that the tail of the answer can be gotten by actually appending the tail of XS to YS. So since I reduce the problem size by 1, I can use wishful thinking to solve this part by just calling the function on the smallest subproblem, and then I just need to figure out how to actually get the one, right? This known as just the recurrence relation, but forget about that for now. So I solve this using wishful thinking. I need to get this one, so that's pair head XS with the. Is that okay? Right, good. So then we can just write the function. So we have return some base case, right? Return base case, base case, base case, base case. If something, then something. If not, now we have to figure out the general case. So what's the general case, right? So my wish was uh, append tail of xs to ys, right? My wish, my this thing is a wish, right? So I'm gonna like, so this thing is my wish. Okay, so that's my wish. So how can I actually combine my wish to solve the problem? I need to actually pair the head of x's, right? That's all. So pair is that clear? Is that clear to everyone? Right. So the main technique here is that you're actually reducing the problem size, right? After you reduce the problem size, you can use this technique known as visual thinking. After you use this technique known as visual thinking, yeah, it's pretty easy. So then you just need to just call the function and done. Okay, now let's figure out the base case, right? Okay, so what's the base case? Okay, now look at how we actually call the recursive function. We call, so append xs ys goes to append tail xs ys. So looking at this recursive call, what's the smallest subproblem that we can solve without actually using recursion? By looking at this recursive call, can you figure out what's the smallest subproblem that you can solve without using recursion? Yes, because you're keeping on going to the tail of xs, right? So when at one point xs will become empty, right? Right? At one point xs become empty. So when xs is empty, when you append an empty list to another list, then what do you get? Yeah, you only get the other list, right? You don't get the empty list, right? Is that okay? Is that okay to everyone? So if is null, then you simply get what? If x is null, then what should you get? Ys. Okay, so that's how you actually solve recursive problems, right? So first step is to reduce a subproblem and then use visual thinking, right? So reducing subproblem and then use visual thinking and then you figure out how to combine the current. You're supposed to figure out how to use the solution to the smaller subproblem to solve the current subproblem and then figure out the base case. So base case can be, can come first or can come last. It's not so obvious, but the most important thing is to figure out that you can actually reduce the subproblem size and use this technique known as visual thinking. Okay, good. Right. So for those of you who are interested in how much time this takes, right? Yes. How long this? Okay. This is about time complexity, which is not the focus of this course. But how long does this take? If anyone knows about time complexity, theta of n. Okay, what's n here? Yes. Yeah. So it's actually taking theta n, where n is the length of xs, right? So for those who do not understand that, it doesn't matter, right? That's not the focus of this course, but just so you know, it takes theta n, and where n is the length of the first list, xs, right? Okay, good. Right. So that's appending two lists. Now let's go on to, yeah. So this one is okay. Right. So this is the append strategy, right? Okay. Good. Yeah. So now I need to talk about one small thing here, right? Okay, so let's actually run through this quickly, right? So I hope this is okay, so I can erase this, right? Is this okay or right? Okay, so I'll just erase this. Or maybe I just keep this here. And I change that one. Okay, so we had XS list 135, right? So we had 1, 3, 5. So we had 1, 3, and 5. Then we had YSS 2, and 4. Okay. So now let's try to figure out what result looks like. Okay. So result is, okay. So now result. So how does result get created? Right. So okay. So look at this function, right? So if I call append, if I call append xs and ys, right? So I call append xs and ys, right? So first of all, it asks, is xs null, right? Is xs null? No, it's not null, right? So then we go into the alternate case, right? So that means I need to create a pair, right? I need to create a pair, right? Right? So then I need to create a pair. So here we go, one pair. Okay, so that's a pair. So what does the head of the pair contain? What does the head of the pair contain? 1. Okay, because we are currently at this place, right? Okay, so we have 1. Okay, then we append the tail of xs to ys. Okay, so that means I need to move the pointer, right? So here we had, yeah, so initially we were here, but now we go here, right? Okay, so now we are here. Okay, so we go append tail of xs to ys, right? So then we come back here. Okay, so I am asking again, is xs null? Is xs null? No, it's not null, right? Is it null? No. So therefore, I come to the alternate case. So then I need to create another pair, right? So pair head xs append tail of xs to ys. So I need to create a pair of head xs, right? Yeah, right? So then I need to create a pair. So what does the head of the pair contain? 3. Okay. Okay. So that's 3. And then I need to append the tail of xs to ys. So I need to append the tail of, what's the tail of this xs now? The pair, the list contain 5, right? Okay. So I need to move the pointer, right? Okay, good. So now I ask again. So is xs, so we are going append xs to ys. So this is xs for now, right? Now this is xs, okay? So yes, this is xs, okay? This ys. Okay. Okay. Now, is xs null? Is xs null? Yes. Is xs null? Who says yes, who says no? Is no, right? Because it's a list containing 5, right? Yeah, so it's not null, right? So if it's not null, we come here. So we need to create a new pair which contain the head of xs, right? Okay. So that means, yeah. Okay. Right. So then we go append tail of xs to ys. Okay. Then what happens? So pair head xs, that would become 5, and then append tail xs to ys, right? And now that something interesting happens. So then xs would be null. So then xs would be null. Because if xs was this one, then the tail of this pair would be null. So xs is null. Okay. So now we have xs is null and ys, right? So is xs null now? Yes, right? Yeah. It is null, right? So then I need to return ys. So that means I need to return ys. Then what happens is very strange, right? So I need to return ys. So then therefore this directly goes and connects ys. Is that clear? So how many pairs did get created? How much? 3. But how many pairs were there in xs and ys both? 5. Right? So if the length of xs is n and if the length of ys is m, how many pairs do get created? How much? Okay, no. If the length of xs is n and if the length of ys is m, how many pairs get created when you call append xs and ys? How many new pairs get created? Only n, right? Yes, only n, right? So n pairs get created and m pairs are reused. Okay? So n pairs will be created like newly, but m pairs will be reused. Exactly? Exactly to everyone? Yes? Okay? Right. So just keep that in mind, right? N pairs will get created, but the pairs from YS will be reused without being created. Okay, good. Now let's move on. Right. So now let's go to the third example, reversing a list, right? Okay. So I hope this is okay. So I'll erase this, right? So we have a function. Okay. So we have function reverse. For example, if I had XS as list, what do we have? 1, 2, 3, 4. 1, 2, 3, 4. So what's the result? What's the result? Yes, if I reverse this list XS, then what do I get? Okay, so these people cannot see the whiteboard, right? So if you cannot see the whiteboard, you can actually bring your chairs front. So it's okay. Okay, so if you cannot see the whiteboard, you can just come front. Okay. Okay. So if I reverse this list, what should I get? Here. Sorry? Yes. So I should get this list. Okay, good. Now, so what's the most okay? So we are trying to solve this problem using wishful thinking. So what's the main step that you want to do? You want to what? What's the main step you want to do? Reduce the problem size, right? If you reduce the problem size even by 1, you can use this technique known as what? Visual thinking, right? To solve the problem. Okay. So now let's try to reduce the problem size even by 1. Even if you can reduce the problem size by 1, you still can use visual thinking. Okay. Now look at this, right? Look at this answer. I look at result, right? So I have this list 4, 3, 2, 1. So I have excess, right? Now if I look very carefully, I see that this part list 4, 3, 2 can be gotten by reversing the tail of excess, right? Yeah, right? Yeah. So I can see that list 432 can be gotten by actually reversing the tail of excess. So can you see that I wanted to reduce excess. I wanted to reverse excess. I reduced the problem size by 1 by realizing that the first part of the list is actually reversing the tail of excess. Yes. First of all, I realized that the first part, forget about the last element of the list, is actually reversing the tail of excess. So I reduced the problem size by 1, right? Because I wanted to reverse excess, but I realized that I can just reverse the tail of excess to get the first part of the list. Is that okay? Right? So then this part can be gotten by reversing the what? Okay. So I had to reverse excess, but I realized that I can reverse. Okay, I should call it reverse, right? Not reversing. Reverse tail of excess. Okay, so I'm going to reverse excess. Now I realize that I can just reverse the tail of excess to get the first part, right? Now since this problem is smaller than reversing excess, right? Why? Because I reduce the problem size by 1, right? Previously I had list 1, 1, 2, 3, 4. Just remove one of the elements, so then I get list 2, 3, 4. That's the tail of excess. I can just directly call the function on the smaller subproblem to solve the subproblem using wishful thinking. Is that clear? So I can use a technique known as wishful thinking to solve a small subproblem. Okay, right. So if I actually reverse the tail of excess, now that's only half of the job done, right? Because I need to figure out how to put the 1 at the back, right? I have the answer to the first part. I already have list 432, but I need to figure out how to add 1. So this thing would be equal to list 432. But I want to get list 4321. So I need to figure out how to put the 1 at the back. So the 1 is actually the head of excess. Now, can someone tell me how to put the 1 at the back? Who says pair? Who says pair? Okay, so my question is, I already have list 432, but I need to put the one at the back. So one is the head of access, right? How should I put the one at the back? Should I use pair? Should I use append? Should I use what? What should I do? Okay, so why not pair? Why can't you use pair? Sorry, you won't get a list. Okay, okay. I mean, there's a null in here, right? There's a null in list, right? Even though you cannot see the null, but there is a null in list, right? So then you said there is no null, but I can. You said that if I use pair, there is no null, but there is a null, right? Sorry. Okay, yes, you're correct. Your idea is correct. Anyone have any other ideas? Okay, so the first answer was pair, list. Okay, so the first answer was this, right? Pair, list 432, which is the answer you get by reversing to the head of x's. So this one would be equal to 1, right? This one would be equal to 1. So shall we draw the box and point diagram for this one, right? So we have a pair, right? So we have a pair and the head is a list, the tail is 1, right? Tail is 1. And then we have a list, right? List 4321. So is this a list? It's not, right? Okay. So a list should be either null. So of course this is not null, right? Or it should be a pair whose tail is a list. So this is a pair, that's correct. But is its tail a list? No. Therefore it is not a list. So you should not use pair, right? So using pair is wrong. Okay. So right, if using pair is wrong, then what should you do? You should use append. Yes, correct. Okay, so let's try to use append and see what happens. Append what? List 432, which is actually reversing the tail, right? 2 to what? Yeah. What should I append it to? Should I append to just head access? Why can't I just append it? Why is this wrong? Yeah, so why is this wrong? Yes, so append will actually append two lists together. Okay, it does not, okay, append should not take a list and some number, right? So head access, okay, in this case it's a number, it can be a list also, but append must take in two lists, right? So you cannot just pass in head X. So will this give an error? If I call append using this, will it give an error? Will it give an error? No, as in if I call append using list 432 with a head access, will it give an error or not? Will it give an error or will it not give an error? Like, so if I type this program into Source Academy and I run it, will it run? Like, will it give an error or what? No, it will not give an error. Okay, because the first part is the list, right? So you would be traversing the list, right? Right. For example, here, right? Okay. So if you look here, right? Here you have a list, right? Here you would have a list, but here is a number, right? So you would be traversing excess, right? You will be keeping on going. And when you hit is null excess, you return the number, right? So would there be an error? There's no error. There will not be an error because even if you append wrongly a list to a number, you still won't get an error because source is bad. No, actually source is good, but we don't have type safety. Okay, forget about that for now. Even if you append a list to a number, you will not get an error because at the end you just return ys, right? Okay. So it's important to understand what source is doing under the hood without just memorizing stuff. Memorizing will not take you anywhere, right? So you must understand what source is doing, and you must be able to write everything by your own and realize what's going on and what's not going on. Okay. So even if you append a list to a number, it will not give an error. Okay. Right. Okay. So let's go back to where we were. Okay, good. So now we were here, right? Okay. So then therefore I need to append what? Okay, so let's try to do this, right? If I append a list mark 432 to head of access, what would I get? Will I get a list? If I append list 432 to head of access, will I get a list or not? Yeah, will I get a list or not? What will I get? There's no name to it, but yeah. So you would get something like this, right? So list 4, 3, 2, and 4, 3, 2. Is that clear? Is this what I get if I append list 432 to head of access or not? So if I just append list 432 head of access, is this what I get? So it does not give an error. But is this a list? Okay, it's not a list, right? It's not a list. Okay, so this is wrong. So this is the wrong way to put one at the back. We are almost there, right? We just need to put one at the back. We are just like so close, right? Except it must be in another pair, right? Okay, so what's the solution? Yes, you need to add list. Okay, so you need to actually append a list of head of access. Okay, so in this case, you would get the correct answer. Okay, so here you would get what? 4, 3, 2, and then when it's null, it points to a list, right? Which is just containing 1. Okay, so now it's correct. List 432 1. So we've gotten the correct answer. Is it okay? Okay, now we can just erase this one. Okay, and then we've done. So we just need to append the reverse of the tail of excess to the list of head excess. Okay, the most important thing that I want to tell you, right, is this technique known as wishful thinking, right? So return something, then something happens. If not, then what? If not, what? What should I do? So I need to reduce the problem size by 1. I realized that I need to reverse the tail of excess, right? Okay, so I need to reverse the tail of excess. Reverse tail of excess. Okay, so this one is the wish, right? This one is the wish, right? Okay, so after I get my wish, then what should I do? So what's left to do? After I reverse the tail, what should I do? Append the append list head, right? Okay, so I just need to append this. Append this one to the list, right? List head access, right? Okay, is that okay? Is that okay? Right. So very easy, right? So you don't need to memorize anything, right? You should be able to write everything from scratch when someone gives you, right? So you don't need to memorize anything. Okay, so let's figure out the base case, right? Right. So what's the base case? So looking at the recursive call, you can see you're calling the reverse tail access. So you're always calling the tail. So what's the base case? What's the simplest case you can solve without using recursion? Is if XS, because you're calling reverse tail access, if XS is null, then you can just return there's no YS here. So you're reversing XS, right? So then just return null, right? Okay. So is null you return what? So if I return and if I reverse an empty list, what should I get? None. Okay. Oh, actually, if you are very creative, you can even just write excess, but just to be clear, right? I just wrote null, right? So because if x is null, you can just return excess. Okay, is that clear? Okay, good. So that's the third example. Yeah. So now let's go on to high order list processing, right? Right. So these are list processing, but we need to go into high order list processing, where we actually work with high order functions, right? Okay. Right. So let's go. Right. So now we want to write a function. Right. So we want to write a function. Example 4. Right. So we want to write a function. Right. We want to write a function called scale. Right. We want to write a function called scale that takes as input a list and a number, and scales every element of that list by that number. So for example, if I have XS as list 1, 2, 3, 4, I need to scale it by k so that my result would be list 1 times k, 2 times k, 3 times k, 4 times k. Okay, so do you get what I want to do here? Right? Okay, so let's try to figure out how to actually try the implementation without looking at the slides. Okay. Okay, so we need to write a function for scale list, right? So function scale. Right. Okay, so we have a list, right? XS and a number k, right? So XS, let's say we have what? 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then we need to get the result, right? The result is list 1. Okay, so 1, 2, 3, 4. Yeah, 1 times k, 2 times k, 3 times k, 4 times k. Okay, so we have a list 1, 2, 3, 4. We need to get, after you scale it, you should get a list of 1 times k, 2 times k, 3 times k, 4 times k. Okay, so this multiplication, not like concatenation or anything, right? Okay, right. So what's the main important step? So again, right, recall, right, is to reduce the problem to a smaller subproblem, right? So reduce the problem to a smaller subproblem, right? Okay, so forget about the figure out the base case, right? Focus on step 2. We need to reduce the problem to a smaller subproblem, and then you wish that you can solve the smaller subproblem by simply calling the recursive function on the smaller subproblem, right? And then you combine the solution small subproblem to solve the larger problem. Main thing is reduce the problem to a smaller subproblem and wish that you can actually solve the smaller subproblem by simply calling the recursive function on the smaller subproblem. Okay, now let's go back. Right, good. So now I just need to try to figure out how to reduce this problem size, right? So I need to scale this list 1, 2, 3, 4 to get list 1 times k, 2 times k, 3 times k, 4 times k. Now if I look at the result, I need to reduce the subproblem size, right? So can someone tell me how to reduce the problem size by looking at result and looking at list? Yes. Okay. So first of all, look at, okay. First thing is I look at list, right? So that is list 1 times k, 2 times k, 3 times k, 4 times k. That is the answer I must get if I scale XS by k. Now, if I look at this list, I realize that the tail of the answer can be gotten by scaling the tail of XS, right? Right. So I reduce the problem size. So I wanted to scale XS. I reduce the problem size by 1 to the tail of XS. I realized that the tail of the result is actually scaling the tail of XS. Right? Is that clear? So I reduce the problem size from scaling XS to scaling what? scale what? XS, oh, sorry, scaling tail of XS by K. So I originally wanted to scale XS, right? I want to scale XS. I reduce this problem size by 1, just by 1, tail XS. Okay. Even if I reduce the problem size just by 1, I can use wishful thinking to solve the problem. Okay, right? Okay, so I already solved the, I already have the tail of result. I just need to put the head of result into place. So how can I actually get the head of the result? I need to do pair head of XS times K. Okay, so I just need to do pair S times K, comma. Okay, right, good. So let's try the recursive function. Very easy, right? It's nothing to think actually. Okay, so we have the base case return something. If something happens, then the base case, right? If not, then what? Then what? Yes. So my wish, what is my wish again? Scaling the tail, right? Scaling the tail of x's, right? Okay, so my wish is scale tail of x's with k, right? Okay, so my wish is scaling the tail. Now that means I already put this into place. I just need to put the one into place. That is head of x's, right, times k. Okay, so I just need to do pair right. That's all. Okay, is that clear? So it's very simple. Just reducing the problem size by 1 can get solve the problem easily. Okay, using this technique known as wishful thinking. Okay, so where is the black marker? So this is my wish, right? This is the most important thing that you should understand. This is my wish. Okay, right. So what's the base case? So looking at the recursive call, you should be able to tell me the base case. So I'm actually calling the I'm actually recursing on the tail of x's all the time. So what is the smallest subproblem that I can solve without using recursion? Yeah. So if xs is null, or rather if x is empty, then what should I then what's the result of scaling an empty list? Basically an empty list, right? Okay. So if xs is null xs, I need to return null, no xs, whatever you learn. Okay, right? So that's all. So you just need to reduce the problem size by 1, use visual thinking to solve that. Then you figure out how to put the current element into place, and then you just need to figure out the base case. That's all. Okay, is that clear? Right. So that's scaling a list. Okay, now let's do the next one. Shifting a list, right? Ah. So I need to write a function called shift, right? That takes in list and adds k to every element. So what's so different from this one and the previous one? So what's so different from the from this one to the previous one? So is there anything so different from the current one to the previous one? So what's different? Yeah, so what's different from this one to the previous one? Yeah, here you just need to add k instead of multiplying k, right? Okay, so here in the same way, I reduce the problem size by 1 by realizing that the tail of the result is actually scaling, shifting the tail of x's, right? Okay, so here I just need to what? Pair head of x's plus k to, oh, sorry, shift to shift tail of xs by k. Right. So now my question to you. Okay. So then if I want to subtract k, do I need to write another function? If I want to subtract k, then should I write another function? If I want to divide by k, should I write another function for that? Yes. So why don't we? So now we are actually adding k, right? We are actually adding k. Previously we had multiplying k, right? So if I want to subtract k, then should I write another function? If I want to divide k, then I should write another function. Then why don't we just oh, give me 1 second. So why don't we just generalize this idea of modifying every single element? That means why don't we generalize the idea of mapping each element to something else? Right? So we have here, here we are adding k, multiplying k, dividing k. We don't need to do all of that, right? We can just write a general function that just does everything. Okay, so that's called an abstraction, a generalization. That's called map. Okay, so that's the first higher order list processing function that we will learn. It's called map. Okay. Yeah. So can you see that? We are doing the same operation. We are doing some operation to every element of the list, right? So why don't we generalize this idea and write one function that can do the same thing? That function that can do the same thing is known as map. Okay, so now take a look, right? So we want to write a function called map, right? That takes as input a list and a function f and applies it element wise to every element, right? So for example, right, if I have xs as list 1 2 3 4, if I call map, right, using fxs, then I should get list f1 f2 f3 f4. Okay, so if I want to add k, then what should I do? If I want to add k, what should my f do? Yeah, if I want to add k, then can someone come up to the board and tell me what f must look like? Yes, f going to. If I want to multiply by k, what should f look like? X times k. If I want to square every single element, what should f look like? X. Okay. So can you see that by just by changing f, we can get a range of functionalities, right? Without actually declaring 10,000 functions to do the same thing. Okay. Okay. So now let's try to write this function. Okay. So I'll erase this because this is pretty easy. So function. Map. Nothing happens, then we close, right? So we have okay, so we have xs as list 1 2 3 4. Okay, so our result should be list. So we have 1, we have 2, we have 3, we have 4. Okay. So then I need to put an f in front, right? That's all. Okay. Is that clear? So I have a list 1 2 3 4. I just need to put an f in front of every single element, and I am done. Okay. So what's the technique we're going to use to solve this problem? We're going to use visual thinking, right? Or recursion, right? I don't like to call it recursion. Let's call it visual thinking, right? Because yeah. Okay. So now, so if I want to use visual thinking, what's the main thing I should do? What's the main thing I should do? So if I want to use visual thinking to solve this problem, what's the most important step that I must do? What's the most important thing I should do? I must reduce the. Yes, I want to reduce the problem size, right? I want to reduce the problem to a smaller subproblem, right? Right? Okay, so keep in mind, right? So the most important thing that you must do is to reduce the problem size, okay, to a smaller problem. And then you just then use visual thinking. Just by calling the function on the small subproblem, you can immediately solve it. Okay, so the most important thing that you must do is reduce the problem size, even by one. Okay, then the magic happens. Okay, now look at this. So I want to map XS, right, to this result. Okay, now if I map XS, so if I actually if I map XS, I should get this result. So looking at this result, I see that the tail of XS, the tail of result, right, this part is essentially mapping the tail of XS, right? Right? So again, right, I want to solve this problem. I reduce the problem size just by one. So can you see I reduce, can you see that this is the answer that I want. I realize that the tail of the result can be gotten by actually mapping the tail of XS, right? So you can very easily see that you can reduce the problem size just by one, to map tail of XS. Okay, I wanted to map XS. I reduce the problem size just by one, and I use wishful thinking to solve this one. Okay, and then what's left? I just need to put the f1 in front, right? So how can I do that? So I already have this part, right? Because I realized that I can just get it by mapping the tail. Because I reduce the problem size by one, I can use wishful thinking just to call the function on the small subproblem, and then it immediately solves itself, right? So it immediately gives me the answer, but I need to figure out how to put the f1 in front. How should I put it in front? Pair, right? So I just need to do pair. I just need to do pair, pair one. F of here of XS. Okay. XS, and then I put at the back what? Yeah, what should I put at the back? Map F tail XS. Okay, right? So the most important thing is I realized that the tail of result can be got by mapping the tail of XS. And because tail of XS is a smaller subproblem than mapping the tail, than mapping XS, I can immediately use visual thinking to call map on the tail. I immediately get this answer. I need to figure out how to put F1 in front. That's basically pair F head XS to the result of the visual thinking. Is that okay? Okay, I hope you understanding how powerful this technique is, right? Without memorizing these function definitions in the slide, you can actually write up these functions within like 2 seconds. If you realize how to use this technique, okay, you don't need to memorize functions. You can just write it on the fly. Okay, right. So let's write the function return something that's a base case. If that's case, then something. If not, then what? Then this one, right? Then I just need to put this recursive call here, right? Okay, so then this one. Okay, if it's not the base case, then I just need to put pair f head XS to map f tail XS. Okay, so what's the base case? By looking at the recursive call, right? So you're actually recursing on the tail of XS. So what's the smallest subproblem that you can solve without using recursion? Yes. So if XS becomes empty, then you can solve it without using recursion. So if you map an empty list, what should you get? Yeah, because there's nothing to map, right? So if you map an empty list, you should get basically you should get the same thing, right? Which is nothing. Okay, is that okay? Is that clear to everyone? Right? Okay. Then you should get is null. Oh my goodness. If is null exists, you must get null. Okay. Is that okay? Everyone, is that okay? Right? Okay, so that's easy. So that's the first high order list processing function that we are going to use. Okay, so next we are going to talk about the next high order list processing function that we are going to use. Before we go into that question, I want you to answer me. Does the function map modify the list in place? Does the function map modify the list in place? What do I mean by this? Okay, I'll explain to you. So I have a list, right? So I have a list, right? So for example, in this case, let's say I have a list. Oh my goodness, no, list. So I have list 1, 2, and 3. So I want you to tell me whether map modifies the list in place. What do I mean by that? That means, does map modify the list here? That means, does map actually return XS, but instead of 1, 2, 3, does it return F1, 2, 3? Yes or no? Okay, so I had 1, 2, 3. If I call map on this list, does it return XS where each of these elements are mapped to F1, F2, F3? Yeah, can you tell me, the girl at the back? Yeah, can you tell me why is this correct or wrong? No. Why is it not? Why is it wrong? Yes, correct. So if you look at the definition, right? So if it's false, if it's not null, you actually create a new pairs. We don't use the old pairs. Okay, so this is wrong. This is wrong. Okay, so if you call map on XS, you actually get a new list. You get a new list. A new list. Right? Okay, you actually get a new list where the elements are like F1, F2, and F3. Okay, so XS will not be touched. XS will remain as is. XS will never be modified, right? If you call map on XS, so XS would be same. So 1, 2, 3. Okay. So if you call map on XS, XS will never change. Okay, because you actually create a new pairs. So you actually need to create new pairs, right? XS will not be changed. Okay. Is that clear? Can you see the board? Right? So XS will never change. It's just that we are creating a new list. Okay. So please don't make that mistake, right? Okay. So the answer to this question is no. Okay. Map does not modify the list in place. Okay. So now tell me. Okay. How can we use map to copy a list? How can we use map to copy a list? Now we realize that map does not modify the list in place, right? So now tell me, how can you use map to copy a list? That means what? So that means like I had XS 1, 2, 3, but now I want a new list called 1, 2, 3. Can you see this is a copy of the old list, right? So I need to copy this list to a new list. But tell me, how can I do that using map now? So tell me. Yes. So what's the f function that I must use? X going to, okay. So I need to use the identity function, right? Because here, right? If I call x, if I call f head xs, that means I just take in the head and return the head. That means I just get a new list where the original values are copied over, but I get new pairs. Is that clear? Right. So keep in mind, map does not modify the list in place. Instead, it creates a new pairs. So we can actually copy a list in this way. Okay. So before we go to the next section, you might be tired. So let's take a 5 minutes break, right? 5 minutes break. Yeah, and let's start at 10:50, right? Okay. I forgot to record. But that's okay. I forgot to record. Yeah. Okay, so we already done filter, right? Yeah, so we've done filter, and yeah, so we want to write a function filter that takes in a list and a testing function that filters the list based on the testing function. Okay, so we've done that, and yeah, okay. So now I hope filter is okay, right? I hope filter is okay, right? Okay, so now let's move on to the next one. So can you recall the sum function that we did at the beginning? So that also we did using wishful thinking, right? Okay, so that's also we did using wishful thinking. I don't know why the projector is so. Yeah. Okay, so that also we did using visual thinking, because now we want to sum the elements in the list, and we realize that okay, we want to sum the elements in the list. We look at the answer, we realize that the rest of the answer can be gotten by actually summing the tail, and then we just need to add the head of excess. Okay, is that clear? Right now, so this is if I do sum. So if I do sum list 1, 2, 3, 4, I should get 1 plus 2 plus 3 plus 4 plus 0, right? Because the base case, right? Okay, so now I'm going to ask you, if I want to write a product function, that means what if I want to write a product function that takes a list and returns the product of all the elements in the list? So that means if I have this list, right? Product list 1, 2, 3, 4, I should get 1 times, 2 times, 3 times, 4 times 1. So what's so different from product and list? So what's so different from product and list? Yeah, you only need to change the plus to multiplication, right? So okay, so what are the changes that you need to do? Yes, correct. So you need to change the plus to multiplication and change this to 1. Okay, right. So again, I'm asking you, do we need to really write another function just to write a product, and write another function to sum, and write another function to divide, write another function to minus? No. Right. So then we need to create an abstraction for this kind of like operation where you actually fold, right? So then this abstraction is known as accumulate. Okay, so let's start. We need to write a function called accumulate, right? Okay, until this point, is everyone with me? Is everyone okay so far? Okay, so now look. Right. Now, this is the very interesting one. You need to understand this very well. Okay, right. So what is this function called accumulate? So we want to write a function, accumulate, that takes a list and a binary function called f, right? And an initial condition that, number one, replaces every pair function with f. 2, replaces null with the initial condition. Okay, so we want to replace every single pair call with f, every single pair call with f, pair with f, pair with f. And 2, we want to replace the null with the initial condition, null with initial condition. Okay, we want to write a function called accumulate that will replace every pair call with f, and it will replace the null value with the initial condition. Okay, right? Again, we want to write a function called accumulate that will take a list and a binary function and initial condition that will replace every pair with f and replace the what? Null value with the initial value. Okay, so for example here, right? So pair with f, pair with f, pair with f, pair with f, and null with initial value. So can you see how we can use this thing, like this thing, to do product, or rather sum? I mean, it's almost the same thing, right? Except like here it's f, but here we had to do plus and minus. So if you want to add, you need to make f what? Add. If you want to do product, then you must make f product. Is that clear? Is that clear to everyone or what? Okay. Right, so let's go on. Right, so this is the most important thing, so pay close attention, because if you get this one, then I think, yeah, the chances of you not getting full marks of the P is like kind of low. So yeah. Okay, so now yeah. Huh. Okay, wait. Okay, no, I just write it down anyway. Okay, so I just write it down. So function accumulate f init access. Okay, so and then we have this function. We have this list access. Uh, yeah, one, pair two, pair three. Okay, so what should my result be? So what should my result be? I need to replace every single pair call with what? F. Okay, so I need to replace this these pair calls with F. So what? So that is what accumulate does, right? Okay, so this one would become F, and then we have a bracket. Then we have F here. Okay, then null should be replaced by? Yeah, what should null be replaced by? Initial, right? Right, so this init. Okay, right? So we just need to turn pair into F, and we want to turn null into the init. Okay, so what's the first step that I must do in this recursive visual thinking approach? I must what? Yeah, can everyone tell me? Reduce the problem size. Okay, so we want to reduce the problem into a smaller sub-problem that we can solve using visual thinking, and then we want to combine the answer to this smaller sub-problem to solve the original problem. Okay, right, so let's take a look. So we want to call accumulate, right? We want to call accumulate that will so this if you call accumulate on excess, right? So if you call accumulate on excess, uh, so this one would be accumulate. Okay, so if I call accumulate on excess, I must get this result. Okay, so I must try to reduce the sub-problem even by one, right? So it's very easy. Okay, now look at this. Yeah, so yeah, take a look. So I want to accumulate excess. Then if I accumulate this excess, I must get this answer. Now, if I take a look at this one, if I take a look at result, right? If I take a look at this part, right? How can I get this part? How can I get this part of result? Like this part. So again, accumulate, if you call on a list, it must replace every single pair by F, and it must replace the initial value by init. sorry, null by init, right? So if I take so I want to get this answer, but I take a look at the smaller version of that answer, this part. How can I get this part? Yeah, so this part, right, is essentially accumulating the tail of x's, right? So I look at the answer. I realize that, oh, that's a bit hard to do. But if I take a look at this part, I realize that I can just accumulate the tail of x's to get this part. Is that clear? And then this part is just accumulate what? Accumulate what? Tail of x's, right? Is that clear? So can you see that? So my original version was accumulate x's, and then I reduce the problem to accumulate the tail of x's. So can you see that the accumulating tail of x's is smaller smaller problem than accumulating the x's? Therefore, I can use what to solve this one? Visual thinking, right? Because this is smaller than accumulating x's. So I can just call the function on the smaller subproblem and then use visual thinking to solve it. Is that okay? That's all. Very easy. Nothing to think about even. Okay. So let's try to write the function. Okay. So we have the return base case. Something happens. Then something happens. If not, then what? What's my wish again? Accumulating the what? Tail of x's, right? So my wish is accumulate accumulate f init and tail of x's. Okay, so by accumulating f init tail x's, right? If I accumulate f init tail x's, then I get what part? Then I get this part, right? But I need to get this whole answer, right? So I already have this part. Then how can I compute this part? How can if I have this answer, then how should I get the large answer? Yes, can someone tell me? I already have this answer, right? By calling accumulate on the tail, I have this part, but I need to get this answer. So how should I do? Yes, is okay. You should not use pair, right? Because here the function is f, right? Right. So you need to use f, not pair. Okay. So you need to just do, because we have this answer, we just need to construct this one. So f comes here, right? F comes here, then what? F of how can I get this one? Head of x is right. Done. Is that okay? Right. So good. Very easy, right? And then what's the base case? Okay, look at how I call the recursive function. So I call accumulate on the tail of x's. So looking at this, what's the uh, smallest problem that you can solve without using recursion? When x's becomes null. So if is null x's, and now what should I do? Should I return null? Sorry? Yes, you should not return null, right? Because what did I say? Accumulate must replace every single pair call with f and replace the null value with initial, not null. Right. So here I must actually return init. Okay? Is that clear? Is that clear to everyone or what? Right? So again, I want to replace every single pair by f. I realize that I can solve this problem by actually first solving this part, and this part can be solved by actually calling accumulate on the tail of x's, and then I need to just put this one in front, which is just putting f head x's and the answer, and then because I need to replace the null with initial, then when you hit the base case, you must return init and not null. Is that clear? So be careful, right? Don't make that mistake. Okay. Right. So then, yeah. Let me get the. Okay, so I hope everyone understood how to accumulate, right? Right, good. So now let's move on. But guess what? Writing accumulate is not the same thing as using accumulate. Okay, so to be a real wizard at using accumulate, you must change your thinking a bit, right? So writing accumulate is not the same thing as using accumulate. Okay, so let's get to this in a bit, right? But first of all, understand how you write accumulate, right? After you understand how to write accumulate, then you must understand how to use accumulate, right? Okay, so let's go. So right now, okay, before we do that, right? So again, accumulate, right? Accumulate requires. Oh, I'll just raise. Okay, so accumulate requires f, init, and access. So access is pretty easy because you just need to pass in the list, right? Initially, you figure out that later, but this f, right? Is this a okay? How many arguments does this function f take? How many? How many arguments does this function called f take? Two. Okay, that's a bit confusing. So look at this one. How many? Okay, maybe I just yeah. So how many arguments does this function called f take? Two, right? So it is known as a binary function. Okay, so if it takes one argument, then it's known as a unary function. If it takes in two arguments, it's known as a binary function. If it takes in three arguments, it's known as a ternary function. If it takes in no arguments, it's known as a nullary function. All right, okay. So forget about that. Okay, now we know that f is a binary function. So that means it must have, when you define f, it must have two parameters, right? Okay. Now, the most important thing that you must do when using accumulate is to, the most important thing that you must do when using accumulate is to name the parameters of the binary function as current and wish. All right, not x and y, not a and b, not c and d, but instead you must name your parameters of your binary function called f as current and wish. Now let's see why you need to do that, because if you do that, solving these questions are actually pretty easy. Now let's see why, right? Okay, first example. Rewrite the sum function using accumulate. Okay, now let's do this. We want to rewrite the sum function. Now what was the sum function? What does sum function do? So what does sum function do? Okay, yeah. So if so if someone gives you a list, if you call sum function on it, it must add up all the elements in the list, right? Okay, so now let's try to rewrite the sum function, but this time using accumulate. Okay, so now let's do that. Okay, I just erased it because it's, I hope everyone understood, right? Okay, so function sum. Function sum excess. Okay, so return so here this should be current current and wish. Current and wish, and yeah, so then something happens, and then something happens, right? And then we have initial value, and then we have excess. Okay, so for example, in this case, if excess is list 1, 2, 3, 4, 5. So for example, just imagine that excess is list 1, 2, 3, 4, 5, right? So we want to sum the elements of this list 1, 2, 3, 4, 5 using accumulate. Okay, so why did I actually rename the parameters of the binary function as current and wish? Okay, so now in wishful thinking, okay, so I think I might. Okay, so I think I might just show you the okay, what I will do, okay, I'll write the sum function that we did previously. So we had the function sum. So we had function sum xs, and then what did we do? So return. So this is normal function, right? So return is null xs. Then what should we do? Return 0. If not, head of xs to plus sum of tail of xs. Right. Now look at this. What was my wish in this case? This was my wish, right? This was my wish, right? Right? This was my wish. So what was my current element? My current element is head of xs. So, oh my goodness, no, I should have put current xs. What am I doing? So this is my current element. Okay, so in my original version of sum, I had my current element and my wish, right? So when you're using accumulate, my first argument, or rather my first parameter is current, my second parameter is wish. So when you use accumulate, actually this current value will be bound to the first item in your list, and your wish is actually the answer of summing up the tail of the list. Okay, so when you're using accumulate, current will be bound to the first element in the list, right? So what your current element here, right? This one. And then your wish, right? Your wish would be actually the summing up the tail of xs. Right? So your wish actually will contain the sum of the tail of the list. So wishes contains sum of the rest of the elements. And current is the current element. Okay, so for illustrative purpose only, I put like current element is 1 and the rest is 1, 2, 2 3, 4, 5. But okay, so the most important thing is that you must understand is when you're going to translate something that you've all written before, right? For here, in here you had current and wish, right? Your accumulate binary function, your parameters must be current and wish. The first element is a current element, which is same thing as this one, and your wish will contain the sum of the what? Sum of the tail of the list. Okay, so now let's see why that actually happens. It doesn't seem, is that even possible that that can happen, that this will always contain the current element, this will contain the wish? Is that possible? Can that happen? Is that possible? I mean, yes, because I'm saying it to you, right? Okay, so let's see why is it that current will contain the current element, and why is it that the wish will contain the sum of the tail of the list? So let's see why that actually happens. It's not magic, okay? It is not magic. So I'll show you why that happens, right? So this one will contain the wish. Okay, so for example, now recall, right? How did accumulate look like? How did we write accumulate? So function accumulate. So function accumulate. So compare sum and accumulate, right? F init and what? Xs. Okay, so what's the base case? What's the base case? If accumulate is null. So if it's null, then what should you do? If it's not, Again, use visual thinking, right? Yes. So your wish was replacing every single pair by f in the tail and replacing the null by the initial value in the tail, right? So then how can you combine that with the current element? You do f of what? Comma, accumulate. Yeah, so this is f in it. That's okay. The main thing is tail of xx. Right. So this one was the wish. This is the current. So can you see the similarity between sum and accumulate? Can you see the similarity between sum and accumulate? So can you see why I told you to write the parameters of the function as current and wish? Because in accumulate, f will be called on current and the wish, right? Right? So f will be called on current and wish. And my current is head xs. My wish is the sum of the tail. Okay? Is that clear to everyone? Right? So that's why I told you to rewrite this is f, right? This is f, right? This is f. When you call f, your first argument, so for your first parameter will be bound to the current element. The second parameter will be bound to the wish. Same thing as here, right? So head, sum tail is accumulate tail. Okay, so how can I turn f into the plus? How can I turn this f into plus? Current plus wish, right? Right? That's all. So I need to do current plus wish here. That's all. Simple. Current plus wish. That's all. So then second argument is the initial condition. So look at the initial condition. If is null, I return 0. If is null, I return init. So what should init be? What should init be? Yeah, so what should init be? 0, right? Okay, so that's all. So I need to return, I need to make my initial condition as 0. That's all. So can you see? Sum can be written in one line using accumulate, but under the hood, it will be called accumulate, which is a multiple line function. But okay, so the main important thing that I want you to understand is how powerful actually accumulate is. Okay, you can write many functions using accumulate because many functions have this form, right, which deal with the current element and the wish. So by changing your parameter names to current and wish, you actually can solve any problem. You can actually simulate recursion. Okay, is that clear? Is that clear to everyone? Okay, so can you see how powerful accumulate is? Okay, so accumulate is very powerful. So if you know how to use it well, then yeah, you are actually in a pretty good position. Okay, right. So I hope you understand why I call it current and wish, right? Very easy. Right. So let's do this again. Okay, now I'll give exercise to you. Rewrite the length function using accumulate. Okay, now you do it by yourself. Rewrite the length function using accumulate. Don't use Source Academy. You write it on a pen and paper. Rewrite the length function using accumulate. Yeah, I'll give you 2 minutes, right? Rewrite the length function using accumulate. So I'll quickly get some water and come. So quickly rewrite the length function using accumulate. Okay. So think in the same way, right? Current and width, right? Okay, so let's start. Right. Where's my blueprint? Okay. So before we begin, I'll write length. Okay, I hope you all can also see, right? So function length xs. How can I do that? So what's the base case? Return what? is null XS, then you return 0. If not, I use visual thinking. First of all, I reduce the problem size by 1 by summing the tail, length of the tail, right? Get the length of the tail of XS plus 1. Okay, right. So now how should I fill in my binary function? What's my current element? So what will be my current? It will be always bound to the head of XS, right? Right. So what's my wish? My wish is the uh, wish is the length of the tail of the list. Okay. So how if I have the wish, if I have the length of the tail of the list, if I have my current element, how can I get the length of the current list? 1 plus wish. Yeah. So 1 plus wish, right? So we have 1 plus what? Wish. What's the base case or initial condition? 0. And then XS. Okay, that's all. So can you see here we have current, but we don't use it. We don't really use current. We just only use one plus, right? Okay. Okay. So is that clear? Okay. So now next example. Can you write map using accumulate? Oh, I just write it. So I hope. Okay. So first of all, before that, is this clear to everyone? Is this clear to everyone? Okay. So now you write map using accumulate. Okay. So now write that map using accumulate. Yes. Now write map using accumulate. So again, I give you 2 minutes, right? Write map using accumulate. So now write map using accumulate. Okay. So who has done? Who has done that? Who managed to write map using accumulate? Yes, but I told you to replace x and y by current and wish, right? Right. So who else managed to write map using accumulate? Who managed to write map using accumulate? Okay. So 10 seconds more. Right? Okay, so let's try. So we have map, right? So function map. So originally we had map, we had f and xs, and then what was the base case? Return. So what was the base case? Yeah, so is null xs, right? If x is null, then I return null because mapping an empty list is null. If not, I wish that I can map the tail of xs and then I what? Okay, so yeah. Yes, so my wish was map f tail of xs, and then I pair what? F of head of xs. Okay, so in here, uh, map f in here, we have that map f tail x is my wish, right? And then head xs is my current, right? Okay, so now what should I do here? So just look at this one, right? And then how can I translate into my binary function over here? What should I do to write accumulate using write map using accumulate? By looking at this one, right? I need to pair f of current to wish. That's all. Okay, that's all. And then my initial condition is null. And then exists. Okay, that's all. Okay, so it's very simple. If you know how to write the function without using accumulate, then translating into accumulate is not that hard. But the key skill is to not write the recursive function first, but rather write accumulate in one go, right? Because like you can see accumulate is like a one-liner. So here there must be okay. Okay, so that's all for accumulate. Now later on when you go home, you rewrite filter using accumulate. Okay, so when you go home, you rewrite filter using accumulate. Okay, and then afterwards you don't use map and filter, but use accumulate to write everything. Okay, right. So next, let's move on to trees. Okay, so I'll erase this part. So is this okay? Like, is this okay for to everyone? Like, writing map using accumulate? Is this okay? So I'll just erase this one, right? Okay, so now let's go on to trees. Okay, so now we have a new definition, right? So we were talking about lists before, but now we have trees. So what is a tree? A tree is also very easy. A tree is a tree of a certain data type. It's a list whose elements are of that data type or trees of that data type. Okay, so again, right, a tree is nothing but a list, right? Except that its elements can be of that data type or trees of the data type. Okay, so again, what type of definition is this? A recursive definition. Why? Because you define a tree in terms of a tree. Is that okay? Okay, so for example, this is a tree of numbers, right? A tree A. Because why is this first one is tree of numbers? Can you try to fit it into definition or what? So is this a list? So a tree of a certain data type must be a list. So is this a list? Yes. But we must check if the elements are of the data type or trees of data type. Okay, so are the elements of this list numbers? we want to know if this is a tree of number, right? So it's yeah. So then the elements of this list are numbers. So it's a tree of numbers. Now we go on to second one. A const tree B. Is this a list or not? So is this a tree of numbers or not? So to find if it is a tree of numbers or not, we first need to check if it's a list. So is it a list? Is tree B a list? Okay. So tree B is a list, but we also need to check if its elements are numbers or trees of numbers. So are the elements numbers or trees of numbers? Right. So we consider the first element, right? So we consider the first element. Is this part, right? Is this uh, a number? Is this a number? Then it must be a tree of that number, tree of numbers. Is it a tree of numbers? Because why? It's a list whose elements are numbers or trees of numbers. So elements are actually numbers. So this is a tree. Okay, so the first condition is satisfied for the outermost tree. Now we go to the second one. So is this a number or tree of numbers? Okay, so is this a number or tree of numbers? Is this a number? No. So it is a it should be a tree of the data type. So to be a tree of data type, it must be a list. So is it a list? Yes. Whose elements are of the data type. So are the elements of this list numbers? Yes. Therefore, this is a tree of numbers. So this is a tree of numbers, this is a tree of numbers. Therefore, this is a tree of numbers. Okay? Okay, good. Yeah. So one thing you cannot consider null and pair as certain data type because null is a tree. So you cannot actually consider null as a data type, right? Yeah. So you must have seen this joke, right? In computer science, like trees go from the sky, right? Not from the ground. Okay. Yeah. So because like you have these kinds of diagrams, right? So they grow from the sky instead from the ground. Okay. So now we should go to something more important. Right. So previously we had that a tree of a certain data type is a list whose elements are of that data type or trees of the data type. But the thing is, you should not use this definition when you're trying to solve problems. Okay, you must not use this definition when you're trying to solve problems. Okay. Instead, you must use this alternative definition that we are going to derive. Right? That is the definition that you must use to solve problems. Okay. So now I'll erase this because this is okay, right? Is this okay for everyone, or shall I erase this? Okay. Okay. So now look at this definition. A tree of a certain data type is a list whose elements are of that data type or trees of the data type. Okay, so let's rewrite again. A tree of. Okay, so for now, I'll actually replace this certain data type with numbers, right? A tree of numbers. So this a list whose elements are numbers. Numbers or trees of that or trees of numbers. Okay, so here we write again a tree of. This is too far away. A tree of numbers is a what? Is a what? It's a list. So what's the definition of a list? No. Yes. So again, like a tree of numbers is a list. But what's a list? A tree of numbers is a list is, okay, then I should say is either a null or B. What? So what is a list? A list is either null or a pair. Pair whose tail is a whose tail is a no. Whose tail is a so what's a list? A list is either null or a pair whose tail is a list. But what does this list contain? No. Okay. So previously we had a tree of numbers is a list whose elements are numbers or trees of numbers. So in this list, if you take the tail of the list, what does the tail of the list contain? Numbers of trees or numbers, right? Now it's a pair whose tail is a list that contains what? That contains what? That what contains what? Numbers or trees of numbers, right? Okay. Okay. So tree of numbers is either null because tree of numbers is a list. So a list is either null or a pair whose tail is a list, but that list will contain numbers or trees of numbers. Is that okay? Everyone is that okay? But take a look at this. Take a look at this. A list that what is a list that contains numbers or trees of numbers? What is a list that contains numbers or trees of numbers? A tree. A tree of numbers, right? So this is actually tree of numbers. So a tree of numbers is either null or a pair whose tail is a tree of numbers. Is that okay? Everyone? So a tree is either null or a pair whose tail is a tree of numbers. And we forgot about the head of the pair, right? And the head is what? Yes, and the head must be, so if the list contains elements that are numbers or trees of numbers, then the head of the list can contain a tree of numbers or a number. Yeah. And the head contains a number or a tree of numbers. Okay, so this is a definition that you must use to actually solve problems, right? So again, a tree of numbers is either null or a pair whose tail is a tree of numbers and whose head contains a number or tree of numbers. Is that okay? So in terms of, okay, so here we talk about numbers, right? But it can be a tree of strings, it can be a tree of booleans, it can be a tree of anything, right? Is that okay? Everyone, is that okay? Okay? Right. Did you understand that? Then, yeah, then it's pretty easy, okay? So let's do this. Okay, so now we want to, okay, erase this. So we want to write a function called count data items that takes as input a tree and returns the number of data items in the tree. For example, this is a tree of numbers, right? So we need to count the number of numbers. Okay, so how many numbers, how many Yeah, how many data items are in this tree? 4. What are they? 1, 2. Okay, so this is also in the head, right? So isn't this a data item? Like it's a head, it's in the head of a pair. So isn't that a data item or what? This one? Why? But it's in the head of but it's in the head of a pair. So that's an element, right? It's an element of a pair, right? I mean it's in the head of a pair, right? So isn't that an element? Yes, that's the answer I was looking for. It is null, but the thing is, a null is a tree of numbers that is empty. If the tree of numbers is empty, then does it contain numbers? No. So you cannot count this null as an element. Okay, in the same way, you cannot count this null as an element. So it has only 4 elements: 1, 2, 3, 4. Okay. Okay, so make the distinction, right? Do not make the mistake of counting like this null as an element, because null is actually an empty tree. An empty tree does not contain any values. Okay, so let's go on. So we want to write the function called count data items that will count the number of numbers in a tree. Okay, yeah, so this is also very easy. So okay, now I'm going to write it here, right? I'm going to write the function here. So function count data items. So function count data items tree. Okay, so we need to write a function called count data items in the tree. Okay, so now we're going to use this technique known as what? Visual thinking again, right? So this is our tree, right? So this is our tree. Okay, so and then I'm going to like put this up a bit. Yeah. So this is our tree, right? Okay, so we want to count the number of data items in this tree. Now we are going to use this technique known as okay, so we only learn one technique. So what's the technique that we learn? We are going to use this technique known as visual thinking or recursion, right? Okay, so to use visual thinking, we must try to reduce the size of the problem, okay, to a smaller problem, right? So now we have this huge tree. We have this huge tree that we want to find the what? Number of data items in, right? But now, but is this tree of numbers null? Is this tree of numbers null? This one? No, it's not null, right? Because it's pointing to something. It is a pair. It is a pair whose tail is a so I just drawing. It is a pair whose tail is a what is this? What is that? What is that? What? So it is a tree of numbers as the null or a pair whose tail is a tree of numbers. Is this tree of numbers smaller than the origin tree? So can we use visual thinking? Can. So we can just call what? Count data items, tail of tree. And then it will solve itself. Then using visual thinking, we have the number of numbers in the tail of the tree. Yes, that's all. So now we consider the head. So what is the head? Okay, I'll put in another column. So what is this now? Yes. So it is a tree of numbers at the null or a pair whose tail is a tree of numbers. So we've taken care of that. And the head contains a number of tree of numbers. But in this case, the head contains a tree of numbers. So is that smaller than the original tree? So then you can use what? Visual thinking. So can you see how powerful visual thinking is? You don't need to think too much. Actually, you don't need to think at all, actually. So when you get used to it, you'll be writing these functions without actually thinking, because they're actually very easy. Okay? Right. So in this case, because the head is a tree of numbers that is smaller than this tree, and because the tail of this tree is another smaller tree, we can use visual thinking to solve this, to solve these things. So how can I use visual thinking? What's the function call I must write to actually calculate the number of items here? What's the function call I must write to calculate the number of data items in this tree, this red color tree, smaller tree? Count data items, what? Tail of a tree. Okay. How can I count the number of data items in this one? Yeah, count data items. Items head, right? Now, one small edge case. Is the head of this pair always a tree of numbers? Yes. So if it's a number, then should we do this? No. Then we should just add one. Okay. Is that clear? Is it clear to everyone? Everyone, is it okay? Right. So let's try this function. So count data items tree. So tree can be, what's the base case? Tree can be either null. So if it's null, then what should you do? Return is null a tree. Then you must return what? 0. Then we must check if the head is a number of tree of numbers, right? Because depending on whether the head is a number of tree of numbers, then what you return should be slightly different, right? But the tail will be the same. Okay. So how can we check if the head of this this tree, right? This tree is a number or how can you check whether it's a number or tree of numbers? Yes, because you can use the is list function because at the end of the day, right? Because a tree is anyway a list, right? A tree is a list, right? Because then you can use the isList function to check whether it's a tree of numbers. Now because the problem is well defined, you can use the isList function. But sometimes even if there is a list, it will not be a tree of numbers. Okay, but because the problem is well defined, you can use list. Okay, keep that in mind, right? Okay, back here. Okay, there we are. Okay, so how can we check if the head is a tree of numbers? We just use what? What? Head of what? Tree, right? Okay, so if the head of the tree is a list, then what should you do? If the head of the tree is a tree of numbers, then what should you do? What should you return? Count data items in the head, which is a smaller tree, and count data items in the tail of the tree, which is a smaller tree. So you can use visual thinking to solve both. So count data items head of the tree plus count data items what? Tail tree. Okay, good. If not, okay, so if the head of the tree is not a tree of numbers, then it's a number. Then what should I return? Yes, 1 plus count date items tail tree. Yeah, that's all. So can you see that you can write any function that you like without actually memorizing any function? See, I don't look at the function, right, when I write this, except I look at the gist tree, and then I realize that you can break down the problem into smaller problems and use visual thinking to solve it. Okay, so you also should not memorize functions. Instead, you must be capable of writing any function that you like on the go, right? Because I also don't look at any slides, right? Because here I don't have the definition of count data items, right? I just wrote it now. Okay, so good. So now that's done. So does anyone have any questions regarding this? Yeah, do you have any questions? Yeah, I heard you talking. So do you have any questions or what? You have a question? No, okay. Right, good. So let's go to the next one. Right, so let's do mapping a tree. So we want to write a function called map tree that will take a tree as input and a mapping function f. Okay, so I'll erase this part, right? Okay, so we want to write a function called map tree that will take as input okay. So we want to write a function called map tree that will take as input a tree and the mapping function f and applies f to every element in the tree. So in this case, we have this tree and we want to get this tree. Can you see that 1 goes to f of 1, 2 goes to f of 2, 3 goes to f of 3, and 4 goes to f of 4? Okay, so we want to write this function, right? Okay, so now I'll erase this because yeah, because you get it, right? You don't need to copy down this stuff. You should be able to write it down anyways, right? Without looking at anything. Okay, so read function map tree. Okay, so we want to map the tree. So what do we want to do? So we have a tree. We want to get this resulting tree where every single number is mapped to f of that number. Okay, so now what is a tree? A tree is either a null or a pair whose tail is a tree of numbers. So in this case, in this one also, this is a tree of numbers. Is it a smaller one than the previous one? So then can you use visual thinking? Yes. So you can use visual thinking to just map the tree of numbers. That's all. Like magic, it will just apply f to every single one. So how can I map this one? Using the function called map tree. Oh, so this is a tree, right? This is a tree. So map tree, what? F tail tree. And how can I map this one? Which is like another smaller tree. This one. How can I map this one? Because it is a smaller tree than the origin one, right? So I can use visual thinking. So how can I map it? Map tree. Map tree one. F head tree, right? Okay. So can you see how easy it is? Right? So here we'll do this, right? So return what? So what's the base case? Trees are the null. So if it's null, then what? If not, we check whether the head is a number or a tree of numbers, right? Right. So how can we check whether the head is a number tree of numbers? So if is list what? No, yeah, head tree. Head tree. Okay. If it's a list, then what should you do? What should you do here? So if the head is a tree, then what should you do? Use visual thinking, right? Then I should just map the head, map the tail, and then I need to create this pair, right? This pair, right? I need to create this pair. I map the head and put it into the head. I map the tail, I put it into the tail. So I need to return a pair, right? Pair. So what's the head of the pair? What's the head of the pair? Map tree F head tree. And what's the tail? Map tree what? F what? Tail of tree, right? Yeah. Oh, sorry. And then, if not, then what should I do? Pair. If the head is not a tree of numbers, then it's a number. So then how should I finish the return call? I need to just F, yes. F. Yes, so map tree. That's all. Okay. So can you see how easy it is to solve any problem that you like, right? Okay. So does anyone have doubt regarding this? Anyone have doubt? So does anyone have doubt regarding this? Okay, no. So let's go on to the next one. Okay. So next one is slightly different, known as CPS, right? Okay. So does everyone understand this? Shall I erase this now? Okay. Okay. So the next one is continuation passing style. So this CPS is different from like what we've been doing, right? It's a completely different topic, right? So just so you know. So right. So CPS, right, can be used to easily convert a recursive process generating recursive function to an iterative function. So what's a recursive? What is a recursive process generating function? So what is a recursive process? Yeah. That has deferred operations. Yes. So one that actually accumulates a lot of deferred operations, right? What is an iterative process? That does not have deferred operations. Okay. Right. So good. Okay. So let me just. Okay. So does this. So is this function a recursive process generating function or iterative process generating function? Why? Yes, because it has deferred operations. Because the last thing that the function performs is actually evaluating binary operator combination and not returning the function call. So it is a recursive process generative function. So for example, I just evaluate like a little bit, right? So we have factorial 4. This will go to 4 times fact 3, right? This will go to 4 times 3 times fact 2. So can you see that like these operations accumulate, right? Right. So this is accumulating deferred operations, right? Okay. So now our goal is to write this factorial function so that it actually does not accumulate deferred operations. So now you learned one method to do it by actually creating a new parameter here, right? Which actually accumulates the result, right, as you go, right? But now I'm going to teach you a method called CPS that gives you a general general framework to convert any recursive process to an iterative function, right, without actually specializing to the problem that you have. Okay, so let's see how you do that. Okay, so now I'm going to do this. Okay, so let's try to fill in this. So fact. So this one was factorial using using a recursive process, right? Okay, so now I'm going to write factorial CPS. Okay, so factorial CPS is almost the same thing as factorial, the normal factorial, right? So here you have factorial n, so I need factorial n here. Okay, so here I had n, so I had also n here. But in addition to that, I have a special function called done. Okay, I have another special function called done. Now done is not here, right? So you cannot find done here, but I have done here. This is the function called done that actually accumulates the deferred operations for you, right? So this function called done is the function that accumulates the deferred operations for you, and then at the end you will actually evaluate it, right? Okay. So the most important thing is you have n here, you have n here, but done is a new function that you have to introduce. Okay, right. So this done is the function that will accumulate all the different operations for you. Okay, now look here. Now I need to tell you that this done, this is the function, right? So this function, this is the function is the function that you must call when you have the answer to factorial n. Okay, so this done function is the function that you must call when you have the answer to factorial n. Okay, so as soon as you get the answer to factorial n, that means you have n factorial, right? Okay, because you're calculating factorial CPS n. So as the moment you get factorial n, you must call the done function using this answer. Okay, so now let's try to see what you should do, right? Okay, so now the base case. So again, similar structure to this one. Like I said, this is a general purpose technique, so you don't need to specialize to every single one. So look at this one. The structure is almost the same. So you have to return the base case. So let's try the base case. So return what? N is equal to 1, right? Right. So if n is equal to 1, do I have the answer to factorial 1? What? 1. 1, right? So if I have the answer to factorial 1, that means I have the factorial to, so in this case, n is 1. So I have the answer to factorial n, right? So this is 1. So then what should I do? Should I return 1? No, I must call done, because done is the function that you must call when you have the answer to factorial n. Because I have the answer to factorial n, because this is 1, I must call done with 1. Okay, so I must call done with what? With 1. Okay, is that okay? So because I have the answer to, because I have the answer to factorial 1, which is 1, I must call done, because this is the function that you must call anyway when you have the answer to factorial n, right? Okay, now come to the alternate case, right? Alternative. Now we have to write the alternative, right? In this alternative, it's the same thing as this one, except you must call factorial CPS, because there are no deferred operations, there cannot be any n times over here, right? Because there are no deferred operations, you cannot write any multiplications outside. So it must be factorial. It has to be, right? It has to be factorial CPS something. Okay, right? Because there are no deferred operations, you cannot put a multiplication outside, right? So definitely it must become factorial CPS something. Okay, then you must call it with n minus 1. You must call it with n minus 1. right? This is the function you call factorial CPS, you call it n minus 1. Then what's this one? Should be done, right? So then this function, whatever you write here, will be called with the answer to, remember, this is the function that you call when you have the answer factorial n. That means factorial, so n, right, is the function you call when you have the answer to factorial n. So when it's n minus 1, this is the function you call when you have the answer to, yes, this is the function that you call when you have the answer to factorial n minus 1, because this is n minus 1 here. Okay, so I will call this. So this will be, I call it wish. Why do I call it wish? Why do I call it wish? Because that's my wish, right? I want to solve the problem for n, but I have the answer to n minus 1, which is in fact n minus 1 factorial. So this wish will contain the answer to factorial n minus 1, because if it's n here, because if I call factorial CPS n, this will be called with factorial n. So if I call factorial CPS with n minus 1, this will be calling the answer to n minus 1 factorial. Okay, so this actually contains, so actually this contains n minus 1 factorial, right? Okay, right. So now look here, right? So we have n minus 1 factorial, right? And we are not in the base case, right? But still we didn't, so at the end we must call done, right? Because we need to calculate the answer to n factorial and call done, right? So we have n minus 1 factorial. How can we calculate n factorial? N into n minus 1 factorial. So n times what? N times what? N times? Okay, so remember, we have the answer to n minus 1 factorial in wish. We want to calculate n factorial. So we need to multiply n by wish, not what, not anything else, right? So we need to multiply n with wish. So we have n here, we have wish. So wish is n minus 1 factorial. Okay, so we have the answer to n factorial, right? Then we must, so we have the answer to n factorial. So then we must what? Call done. Done. That's all. Okay, so that's how you actually convert any recursive process generating function to an iterative process generating function just by using this formula. Okay, so so it's actually kind of magical, right? Like I have this function called done, and I'm like calling it, like, does it even make sense? Okay, let's see why it makes sense, right? Okay, so I'll show you why it makes sense, right? So now keep this in mind, right? Okay, so now I'll show you why it makes sense over here. So now we have factorial CPS. Okay. Oh, by the way, in this one, right, you call it with, so the way you call this function is different from here, right? So in here you would call factorial. Let's say you want to calculate factorial 4. So you would call it with factorial 4, and that's all, right? Right? Here, so there we call factorial 4. Here we have to call it differently, because why? We have another function, right? We have another parameter, right? Okay, so here actually you call it with like this, factorial 4 and another function. This must be a function, right? Actually, this function is pretty simple. You must call x going to x. Okay, so this function, right, the done function, the function that you call it with, is actually the identity function. Okay, right? So here, so this should be factorial CPS, but yeah, I mean, you get it, right? This is factorial CPS, right? So here, when you call factorial CPS, it must be with the number that you want to calculate factorial, but here the done function must be the identity function. Okay, now let's see why that this actually is very beautiful and it makes sense. Okay, now I'll draw it here. So people who cannot see, you can like come here, right? So we have a function called factorial CPS. Factorial. Okay, I just call it fact CPS because it's too long, right? So we have fact CPS. Fact CPS. Let's say we want to call it with 4, right? So we have the function x going to x. Okay, let's use a substitution model, right? Okay, so fact CPS 4. So is this a base case? So it's not the base case. So therefore, it's the alternate case. So then I must call again fact CPS, right? What should I call it with? 3. Right. So now it should be that wish something, right? Now look what happens, right? So we have wish, right? And then done n times wish, right? Okay. Now I'm going to write this done a bit below. So this done function would be x going to x, right? Here this we call it with x going to x, right? So this done function is x going to x, right? Okay. Here I'm going to put it here, x going to x. Okay. What are we going to call it with? Yes. So that we're going to call it with 4 times wish. Is that okay? Okay. So now we go to the next step. So next step would be fact CPS 3. So is it the base case? No, right? So we go here. So we have fact CPS. So what should I call it with? 2. Okay. Now this is my done function, right? So this is my done function. So that done function comes here, but I need to put this wish outside of it, right? Okay. So that becomes wish right? Then my done function is this one, right? So I put wish, right? And then so I have x going to x. So here I have 4 times wish, right? So here I have what should I put here? 3 times wish. Is that okay until now? Everyone? Okay, is that okay to everyone? Right? So then we come here, right? So fact CPS 2. So 2 is 2 the base case? No, then we need to go to the alternate case, right? So so I don't have space, so I write it here, right? Then can you see? Oh, that thing's cut, right? Okay, it's okay, I can write it here. So we have fact CPS. So 2 comes here. So this is 2. So 2 minus 1 is 1. Right? So we have this one. And then we have what? Then it's wish, right? Okay, so then this must come down. I need to put this is a done function, right? So like this is there. So this is my done function. Yeah. Then this one, right? X here is what 4 times wish, right? And then this one would be 3 times wish, right? And this one would be okay. Is that okay? Is that okay, everyone? Okay. Yes. Yes. So then we have fact CPS 1, right? So 1 comes here, right? Then you call it with done one. And now what happens? So you're gonna so you're gonna call this function, right? With 1, right? So 1 comes here, then 1 goes here, then 2 times wish, then 2 comes here, then 2 times 1 comes here. So 3 times 2 times 1. Then that comes here, then that comes here. So 4 times 3 times 2 times 1. So that comes here, that comes here. So 4 times 3 times 2 times 1. That's how you convert any recursive process to iterative process. Yeah, that's all. Yeah, this technique is very general. You can actually convert any recursive process you like um, uh, to an iterative process. Okay, so yeah, okay. So the most important thing is for you to understand how to use CPS, right? So in CPS, you need to put a done function. The done function is the function that you must call when you have the answer. So in the base case, you can directly call, and then if not, then you must write the alternative case in the following way, right? So you must call done when you have the answer. Okay. Okay, is that clear, everyone? Right. So this is like one of the most beautiful things I have studied in CS, right? Uh, Sorry. Yeah. So this is a very beautiful thing I have studied in CS, right? Right. So in this way, you can actually convert any recursive function, any recursive process generative function to like an iterative process. So if it is a bit confusing, you can actually put brackets here, right? Right. The same thing, but okay, it's just easy. Okay. Right. Yeah, so does everyone understand this? How we actually construct this done function? This done function actually stores the default operations, right? So this done function will store the default operations, and at the end, you actually unleash all the default operations like a waterfall, right? So at the end, after you store all the default operations, like okay, it's like you stack a lot of dominoes next to each other, and then at the end, like you tap one domino, then it's like a waterfall, it unrolls. And that's the same thing as what happens over here, right? So in here, like at the end, you call this function with 1, so 1 comes here, then it comes here, so it becomes 2 times 1, then 2 times 1 comes here, then it comes here, so 3 times 2 times 1, that comes here, that comes here, so 4 times 3 times 2 times 1, so that comes here, comes here. So that's what you return at the end. So after you evaluate done one, that becomes, this one will be equal to 24 for factorial, then that is the one you return outside. Okay, so after you do this is outside of CPS, right? Then you return 4 factorial. Okay, yeah. Okay, I think I'm out. Okay, I took like 11 minutes more. But yeah, but I hope it was worth it. I hope you understood what CPS is. So in the lecture slides, right? Now you should be able to write any, yeah, yeah, you should be able to write, like for example, here they have done, they have converted append, like for here, in this case, this append is what? A recursive process function, right? Oh, no, sorry, before this one. This one is a recursive process generative function, right? Because like you have this pair outside, right? So this is a recursive process generative function, right? That's true, right? So if you want to convert this into an iterative process, you can use the CPS. So you can go home and try how to do it into CPS. This is basically CPS version, but I don't recommend you do this way because you change this function to done. Then it's actually easy to understand. You convert C to done, and then you can just do the same thing. Okay. This C, I don't like calling it C at all. I call it done. Okay, so this is done. Okay. Yeah. So then same thing. So this is done. And then this is wish, right? Don't call it X because like you need to know what is this and what is that. So this X is wish and this is C is done. And so this is wish, right? Okay, so you can like go home and do it by yourself. It's actually pretty easy, nothing much. Okay, and yeah, so you can convert any recursive function this way, factorial, yeah, same thing. Okay, summary. So this processing we actually learned how to use wishful thinking to write length, append, reverse, how to write high order list processing like map, filter, accumulate, how to actually work with trees. That's also using wishful thinking. Then how to do CPS. Like these three are like wishful thinking. This is like something beautiful, whatever. Right. Yeah. So the main important thing takeaway is that using wishful thinking, you can like write a lot of things without memorizing. As you can see, I didn't look at the definitions of anything, but just looking at how to reduce problems into smaller problems, you can use visual thinking to solve them. Okay, I think that's it. Yeah, that's it. Okay, so that is it. I'm sorry for taking like 30 minutes more, but I hope it was worth it. Okay, so yeah, that is the end of the class. So what you can do now is you can go ahead and have lunch and be back at 2:30.